Ding.
All right, thank you very much. Yeah, thanks for the intro. I hope you can hear me okay. Give me a sign in case not. But then let's get started. So yeah, this is kind of what I want to talk about, and that is something that is very dear to my heart, which is kind of the state of machine learning, now called AI, for science and engineering. And I think a lot of what you're gonna hear is like born out of a deep enthusiasm for technology and for the dream of machines learning and helping us humans. And on the other hand, I think there will be some gleams of disappointment of what the world makes out of that technology and sort of in which direction some things are heading. So I'm looking at exciting in everyone listening to this talk, sort of these conflicting feelings of um, let's be fascinated by technology and also use it for good, whatever that means, or at least try to be useful with it. And perhaps if there's one takeaway message, then it's like let's be mindful of what we're using tools for, including AI, and ensure that what we achieve by that is actually something that's useful. And that definition is left as an exercise to the reader. Yeah, you heard a quick introduction, but here's a little bit more about myself. I have a background in oceanography. Known in some circles for writing an ocean model called Veros. That's a Python ocean model that works on GPU thanks to a JAX backend that scales quite similarly to underlying Fortran uh, pretty energy efficient when you run it on GPU. It works on multiple GPUs, and it's that was kind of when I had my 5 minutes of fame on Twitter and got a little bit attention there, and then I transitioned a little bit more into machine learning, and I did this study on rogue waves, which I think came up a couple of times during the seminar series as well, where I try to infer the causes of rogue waves with machine learning as a data analysis tool. And there'll be a lot more about that in this talk. Then a little bit about my current employer, which is I can't really separate from this topic because that's so much on what we work on at Pasteur Labs is tied to that. So Pasteur Labs is a private company, a startup that's distributed, and we view ourselves within this paradigm of Pasteur's quadrant, which is really a way of characterizing science where people could be very application oriented but not be interested in fundamental understanding, or you could be only interested in fundamental understanding and not in applications at all. And I think there's plenty of examples of inventors and engineers and scientists filling all of these categories, and where Pasteur's quadrant is called that way because Louis Pasteur is someone who was both very considerate of usage and applications of methods, but also fundamental understanding, and that's what we strive towards in our company. So this is really a high-level intro where we are very outspoken about our approach to use-inspired research and our both our vision and mission that are defined in abstract terms, and then we can get slightly more concrete. I think we can jump right to the mission, where it's really about a lot what we build is about bringing machine learned surrogate models into industrial R&D environments. So it's really fundamentally about simulation and augmenting that with machine learning and other technologies to achieve something like a 21st century simulation stack, also using differentiable programming and probabilistic programming and different styles of computing and causality where really everything is on topic to uplift the field of simulation into the 21st century and like the AI age. Okay, with that somewhat long-winded introduction, let's get into the topic. And I like to use this as a motivating example because it's often something that people are familiar with. So there's AlphaZero, which made headlines, I think it's almost 6 or 7 years ago, which was really a defining moment for AI, where we had suddenly had this chess bot that was taught by self-play and that was playing, well, far superhuman, but also far superior to existing chess engines. And people were looking at how is AlphaZero playing. And this is a plot of the openings that it rediscovered from self-play that we have names for, but of course the bot doesn't have a name for them. And the which openings are preferred by the bot over how long of a training time. And you can analyze this, and people have looked at this in detail. And there's one particular example where the French defense, which is a reasonably popular opening, was discovered at like the 2-hour training mark and played quite a lot. And then the model, as it progressed and got better, it stopped playing the French defense. And then you had human players wondering what's wrong with the French defense. And I like this example because it shows that just predicting something is not the same as understanding something. And perhaps even better than the word understanding is like prediction is not the same as causality or even knowing what the winning strategy is doesn't always allow you to exploit that. So against humans, you can still open with the French defense and just play as well as before. And of course, this artificial example gets amplified many magnitudes over when we're looking at real world systems, just like with all their complexities and feedback cycles and noisy data and which is as far as you can get from something like a game with perfect information. So AI is really in a position where there's these miraculous successes and at the same time not a lot of progress in terms of that understanding and really usefulness for humans specifically. And so to not throw the baby out with the bathwater, ideally a useful AI model would contain a couple ingredients like the ones listed here. So an understanding of causality so that it can transfer to us humans so we understand a phenomenon. Compatibility, so really being a drop-in replacement for a lot of existing simulators, for example, and I'll get to that more later, is really a desirable property. Also to get in a situation where you can fuse your models and data and existing simulators, which is really attractive from that perspective. And finally, reliability just can't be an afterthought. And this is something that I like to summarize as AI that speaks our language, because it's really about creating these human machine teams that elevate each other rather than having a predictor learn something and then not really knowing what to do with it. So this talk here is really in two, split in two. So the first 60% or so is about science, and then the rest is a bit about engineering. Since this is an academic audience, I thought you might be more interested in the scientific part. And this is where I present some of my personal research that I've done before I joined Pastor Labs, and then in the engineering part, I will be more about my current work. But I think we can find a red thread through both of those parts. A bit more of motivation here. So now this is about science specifically, and I think something that an observation that I've made, which I don't know how profound it is, but I would like to share it, which is machine learning models are often either way too specific to one problem at hand, or way too general to be useful. And I think that holds across science and engineering. And in this case, let's talk specifically about science. I'm going to show you some examples, but this is really not to single out researchers or specific works, which is really not something I'm looking for. It's more like to give a motivation for what I mean by that. So models that are totally specific, for example, this is just what comes up when you go to the EGU website, a conference in geophysics, and search for LSTM, which is really a bunch of talks, oral presentations, showing how you can apply one specific algorithm to a domain-specific problem, which I would argue is not very useful to do science, because this is not really, I don't want to be the gatekeeper of what is science and what is not, but I think it's fair to say that this is not addressing questions with scientific inquiry, where it would be more obvious what's going on if we would replace those machine learning methods with something like polynomial fits, which is conceptually similar, where that technology is more obscuring than enlightening. And totally general, I think is there's plenty of examples too. So this is one recent work where someone trained on a lot of graph data and then had a general model that could predict across graphs, or something like very general time series forecasting, which, don't get me wrong, it's useful to predict sales in something like a commercial application, but it's not a useful tool for scientific inquiry. So I don't want to dwell on these examples too much. It's more like about the general theme that there's a compromise, or there's an observation that both extremes are not desirable, and then that must mean that there must be something in the middle where we actually have a region of usefulness. And I think, well, a great example is AlphaFold, which just a couple of weeks ago won the Nobel Prize, essentially, where we are applying general methods to a class of problems that is not everything. AlphaFold doesn't predict how other things fold. It's really specifically about proteins, but about a large class of proteins. And I think that is, you can argue if that's science or engineering, but I think that's a very useful position for an AI model to be in. For science specifically, one problem is that the goal of machine learning is just often not discovery. And discovery means us humans learn something. It doesn't mean the machine learns something and can predict it now. It means that we can write knowledge into a book and put it into the library and advance the canon of knowledge we have as humans. So this goes a bit now into my research on applying that frustration to rogue waves, and to learn the causes of rogue waves from data, which is, I think, where I'm at least trying to position myself in the middle category, and being very mindful about the choices that I made, and like the class of applicability of these methods. So in science specifically, I think it's good to go back to the basics occasionally and think about like what are the actual goals of science. And I think parsimony specifically is an excellent guiding principle in scientific machine learning, where it's not so much about predictive accuracy, but much more about with the minimum amount of free parameters to explain a phenomenon well, which is tied to something like Occam's razor, or like the principle of least action, and really pervasive in science. And this is something that has ties to causality as well, and that we can exploit to define and build AI that can teach us something. Now, this is a figure from the paper that I'm describing here, where it's really about the whole journey from raw data, in this case, sensor measurements from buoys, via causal machine learning and via black box neural networks and model selection and then symbolic regression into an equation. And that I think is an interesting alternative to have machine learning models that don't output a predictor, but they actually output a human readable equation. And this is where this paradigm of AI that speaks a language kind of comes from, and where this ties back into that. So the language of science being usually mathematics and equations. And if we manage to build AI that speaks that language natively, we are in a much better spot in terms of actually using that to advance our knowledge. So I assume that a lot of people in the room know what a rogue wave is. I'll go very briefly about that because it's also not really about that example, but more about the general paradigm. So a rogue wave is really, in this definition, an unlikely wave. So it's really just anything in the tail of the wave-height distribution, and where we actually don't really know how that tail shape it looks like and what parameters it depends on. When we're like going to really small probabilities, where like in this linear plot, it's actually vanishing probability. And so we're trying to find really the likelihood of measuring a wave that is much larger than the significant wave height, which is sort of the average wave height, and what parameters does it depend on? And specifically, which forecastable parameters does it depend on? So we can actually give something like a risk assessment, which is both fostering our understanding, hopefully a little bit, but also leading to something like an operational forecast that maybe something like a shipping company could use to plan their routes. I don't want to go too deep into the theory on this. There's a couple different theories, and that's kind of the point I'm trying to make, where there are existing competing theories. There's blank spots where you kind of know that things are incomplete. And I think this is a very strong position for AI to make a difference, where it's like you have a couple of theories, but you can choose among them, and you have a reasonable amount of data, where really we can use machine learning with its pattern matching abilities to help us solve that conundrum and really pick a theoretical solution, or like come up with a new one that's like slightly modified from what we already know. So the goal here is really to find a predictive model that's also a causal model. So it's not just about being a good predictor, but also using causal connections. And the goal is twofold. So one is the better forecast, and the other is like foster our understanding. That's kind of what I just described. In that particular study, I used buoy data, which is just a lot of 1D time series, essentially, from the west coast of the US, and also some in the open ocean and in the overseas territories in like Hawaii. And the first step is like assemble that into a data set, which means really just map C-state parameters to labels, which is like the observed wave height. So we can learn these connections. What are the connections between forecastable parameters and observed rogue waves? And that was one study that we published. And then we can go to work and use that data to actually build these causal predictors. And in causality, something that almost sounds trivial or pointless when people start out with causality is that the importance of writing down a causal graph, which is really, in my experience, 80% of what it means to be doing causality. It's just about making implicit assumptions very explicit and once you have written something like that down, it can be challenged by other people, and you can also embed this knowledge into your models that you're building. So I think this exercise is really something that shouldn't be skipped. And we use that in this case to write down all the hypothesized causes for these waves, and then only include the direct causal factors into the prediction, which is already a regularizing exercise. Then we train these black box models on the causal parameters, and I think something that is interesting with causality specifically is that we have these conflicting goals between learning the causality of the problem, which means effect sizes and really the strength of these arrows in this graph. But it also means once we're confronted with real world data that is noisy and model assumptions that are imperfect, so it also means we at the same time have to find a model that predicts well, which is really creating this almost a push and pull between these sometimes conflicting objectives. So we can't just find a model that's perfectly causal consistent, because the noise in the data might not allow us to identify that model. At the same time, we can't just go for the best predicting model. And that's that multi-objective process is really what this whole publication is about. So it also means leveraging the very powerful pattern matching and data consuming abilities of something like a neural network. So we do train neural networks on this causal data. And then after training a lot of different models on a lot of different data sets with a lot of different settings and regularization parameters, we measure how causally consistent each of these trained models is, and then select one. So you can read all the details in our study. So, but to just give you an idea of how this works is that the main fact that we exploit is that a causally consistent model is one that is invariant under shift in the data. So let's say we want to learn a theory of gravity, and for that we make measurements on Earth, just how different objects fall. If we have identified a causal model for how gravity works, then it should be possible to go to the planet Jupiter or the middle of the Milky Way and repeat the exercise and get the same results while plugging in different parameters. And the exact same idea applies here, where we measure, once we partition data into different environments, so some in deep water and some in summer and some in winter and some in like spectrally narrow sea states, and all these different environments on the left side, we can measure how invariant the models are under these distribution shifts. And that is one criterion that we use to quantify the causal consistency of the network. So we do that for every single network. We also quantify how well it predicts. And then this is really where kind of the magic happens, or the most manual step in this is selecting among the models. And this is where parsimony comes in as a guiding principle, where we say we want to select a model where making it a little bit, where a much better prediction comes also at the cost of a much larger causal inconsistency. So it's really about the idea that once you have identified a model that is causal, then there is not that much improvement in the predictive capabilities to be had by relaxing that restriction on causality, because at this point, you're essentially fitting to the noise in the data. So increasing the complexity of the model when it's already causal is not going to give you very much in terms of extra predictive accuracy. And that's kind of the lines along we think to select this point, which is close to like this inflection point of the Pareto curve here. And then the final step, now we're left with an approximately causal machine learning model, so a black box predictor that we can analyze and all. But I think the most exciting step then is to take that and regress it into an equation, which is what we did here. So this is a method called symbolic regression that allows us to learn an equation from data. And in this case, it learns the equation on the inputs and outputs of that machine learning model, which is based on fantastic work by many people. For example, here Miles Cranmer, who developed that software that we're using. And so this is another motivating example now from astronomy or like celestial dynamics, where this paper shows that symbolic regression can rediscover the laws from gravity just from data how different planets move around the solar system. And I think for this paper, they actually used the original data that Johannes Kepler had access to. So it's a little bit going into the direction of the dream of science, where we essentially can learn equations from raw data with machine learning. And in this case, we're applying this. Oh yeah, here it finds the laws of gravity up to like a rotation or so of the vector and like a constant. So it's actually the same as the laws of gravity. So applying that to the neural network leaves us with that equation for the likelihood to generate rogue waves in a given C state. And there's many things that are a bit weird with that expression, and I know that it's not correct in any sense of the word, but I still think there's a lot to it where you can actually, at least now we have the ability to look at these terms and like analyze them. Whereas if we had stopped with the neural network, then that scientific process would have kind of also stopped at that point. And by being able to write down an equation like that in one line and talk about it, I think we as scientists at least are not quite throwing out the baby with the bathwater. So there's some terms in here that are borderline nonsensical. And then there's some terms here where we can speculate a little bit about the meaning, which is like the yellow ones. And then the most satisfying ones are the green terms, where essentially the first two terms in a bracket are a Taylor expansion of a term that we have hypothesized would show up there to first order. So I think, and this is, again, this is not injecting any knowledge about that equation except the causal structure by selecting features and like selecting the model that it's based on. So it's really, it rediscovers this expression from data and then adds some more that we can chat about and while also predicting better on our data set than any other theoretical distribution or so. And I think that's at least a decent spot to be in as scientists who use AI as a tool. And yeah, so that's kind of the overarching theme here, where I think that AI provides real-world utility if it speaks our language, and in this case, it's mathematics and physical models and causality, but it depends on really on the application. When it exploits the characteristics of existing systems, in this case, the causal structure and parsimony as a guiding principle, which also ties in a little bit into like the intermediate complexity of AI that is a sweet spot where it's we want to exploit these characteristics without prescribing them. I think that's maybe another way to look at it. And finally, causality is really a necessary ingredient to make meaningful models in science. Okay, let me check the time real quick. All right, I think that's all right. So that was the part about science. Now I have a couple more slides about engineering, where it's more about what we do in our day-to-day work at Presto Labs and the products that we're building, which is really about simulation and about augmenting simulation with AI and machine learning, but also in a way that provides real-world utility. Just that the objective function is usually a little bit different than it is in science. So we can start with the same list of ingredients, really, where let's do it like that, where causality is also extremely relevant, especially when it comes to finding something like optimal interventions or optimal control or so. But I won't go into too much detail on that. We work quite a lot on building systems that allow us to be compatible and reliable in simulation specifically. I'll expand a little bit more on what that means in practice. But yeah, some applications that we're working on is, for example, real-time prediction. So just simulators that replace essentially existing simulators, just being much faster in real time. End-to-end optimization with something like a gradient-based optimization scheme, but also data-driven methods of any kind, multi-fidelity, uncertainty quantification. Just the mere act of incorporating data into an existing simulation is something that is unlocked by these methods, and that's just such a powerful paradigm. And again, there's a couple of problems with AI in engineering too, where it's not so much about the conceptual issues, but more about the capabilities of AI that are pushed very strongly by certain academic environments and also, well, industry labs that publish, but what they publish is usually not a fit for the real world in any meaning of the word. So a really fundamental problem when it comes to bringing surrogate models and AI-driven simulators into the real world is geometry, where it's really apparent how far we are from models that could tackle something like these three examples, like very large and unstructured simulations, which are just very hostile to the way a lot of neural networks are implemented with like fixed stride convolutions or so. Coupled mechanisms where there's really very little research on coupling something like multiple surrogate models, or even like evolving meshes that requires remeshing. Yeah, I don't want to sweep under the carpet that there are success stories. Also, when it comes to surrogates, where something like this is from a paper called GraphCast, which is for numerical weather prediction, which is really one of the few success stories of surrogate models, where we're now at a point where learned models are competitive with large mechanistic models. And this is somewhat how it works. The mesh is interpreted as a graph, and then we add multiple layers of that mesh in different resolutions, and that is kind of like a multigrid method, but on the surrogate level. And it works great in weather prediction, and then there's other works that extend that to more unstructured surfaces. Like here, this diffusion net, it's more like a kernel method. And if you read the papers, that all sounds fantastic. And then you read the paper some more, and then we say, here we show how we scale mesh-based predictions to complex 3D systems with thousands of nodes. And if anyone has ever had touch points with real-world systems, then thousands of nodes is really not even the smallest textbook example. And where in the millions of nodes is where it gets interesting. So this is several orders of magnitude off a commercial scale. And then there's other examples where, for example, NVIDIA is very vocal about their Fourier neural operator models, and there's this whole platform called NVIDIA Modulus, which is fantastic science and very inspiring work. And there's also an NVIDIA weather forecasting model based on FNOs that is, yeah, published like this, and oops, it doesn't work on unstructured meshes. So even the very successful examples are still quite far from being in the situation where they're compatible and where they're reliable and where they fit the categories of speaking our language. And that's really the bitter lesson here that we need to accept, and that we're working very hard to address. And then yeah, I don't want to get too deep into this one, but it's really also the whole life cycle of a machine learning model from paper to production essentially is incredibly long and involved, and requires several stages of checkpoints really to ensure that a model is well behaved, also that it generalizes well and that is applicable in a decent range of circumstances, and that it doesn't break if you show it new data, and that it works in production, and that it's fast and cost effective, and all of these things that are not rightfully not part of an academic paper or so. So putting these things into production is really a tremendous effort. Yeah, here it's even pictured as a knot, which I kind of like. It's like the Gordian knot that's really impossible to untangle. Um, and finally, something that is very dear to my heart personally as a big enthusiast of auto differentiation, where it's often overlooked that uh, machine learned models are also attractive because they are differentiable by construction, essentially, since they're trained by gradient descent. So we can also exploit that differentiability in production, right, at inference time. So for example, the code here on the left-hand side is a very simple optimization procedure in JAX, which is a machine learning framework in Python, where we example optimize the performance of a simulation with respect to something like the design parameters going into it. So it's really about inverse design or shape optimization. But there's quite a few practical problems with that. If you look closely, where it's really about how do we even implement these heterogeneous operations like applying a parameterization or creating a geometry, creating a mesh. What does that How do we engineer this, and how do we ensure that this is resource effective? How do we incorporate code that's provided by the end user? How do we handle memory problems in something like this pipeline, which makes it almost impossible for academics to experiment with these methods and like develop optimizers that work in these settings. And we're clearly facing the same problems, and that is one of the things that we're working very hard at, to build abstractions that are autodiff native and allow us to execute all of these steps in this pipeline, for example, on different machines, but in a way that doesn't compromise on the research code that you would write to interact with them. And that's really one of the value propositions that we have, where it's about bringing these methods that are enabled downstream of surrogate models into an environment where people can experiment with them. Because even the act of experimentation right now is such a high barrier to overcome that most people just don't bother. And yeah, this is the last slide that I have. So if I had to summarize it, then yeah, something that's just really important is to have surrogate models that work on actual data, that work in actual environments, that are not cherry-picked, that share the same interfaces as existing simulators, that exploit other technologies like autodiff and uncertainty quantification, and don't stop at training a model, because that's really the easy part. And integrating these models and interacting with them is something that requires so much more effort and thought, and is really uncharted territory in a way. Yes, and finally, there's the hope that we can do well if symbolic regression and discovering equations is the science way of producing knowledge, then I think the engineering equivalent of that is something like overcoming simulation to real gaps that exist. So what is a system that we cannot simulate today? Maybe because it's experimental, or because it's too expensive, or because it's just too intricate. The geometries are too complicated. Making these systems possible to simulate is really, in a way, the engineering equivalent of generating knowledge that you can write into a book. So I think that's kind of the red thread, and I'm trying to pull through here, and something that motivates me a lot in this this work. So yeah, thank you all for bearing with me. I know that was a lot, and happy to answer any questions you might have.
Thank you, Dion. Okay, let's start with our friend online. Any questions from our audience online? Matt, are you online? Okay, he's not there. So, any questions from?
Hi.
Say it again.
Hi, I have a question.
Okay, can you share your screen?
I'm sorry, I'm not able to share my screen right now.
Okay.
But I want to thank Dr. Häfner for the very inspiring presentation. And I have a question on whether you can comment on like the performance difference between like black box machine learning models compared to that you learn a specific equation from the data.
Yeah, I'm happy to. I just have to ask you to define performance for me.
Yes. So I think the performance is quite hard to evaluate, but based on like, for example, based on your training data and the test set, like what would a more like black box machine learning model perform with some of the metrics that you use compared to the more causality based model that you developed?
Okay, then I'll assume that you mean something like accuracy and not compute performance, right?
Yeah. More like accuracy and
Yeah, okay, then we're on the same page. Yeah, I think that requires a nuanced answer. Just like most of the things I just presented, where it's really important to ask performance in which data set, or like in which situation, where sure, if we're predicting on data that is from the training data set, or at least looks very similar to the training data set, you will always get better performance out of a black box model. But that's also kind of beside the point, where our restrictions to a physical model are not to predict the noise in data very well or so, but more to work in a lot of different situations. So I think as scientists, we should prefer a model that works well at close to coasts and also works well in the middle of the ocean, or at least works well in the middle of the Pacific and in the middle of the Atlantic, where only that will give us any reasonable amount of confidence that we actually learn something about the physics of the problem. So I think it's a little bit beside the point to even measure that. Where I can see if that seems like dodging your to answer, but I would be careful just even making that argument. And sure, you can look at the numbers from the paper and the differences are not massive, but this is just one example out of many. So if we're talking about a general philosophy and how to train models, then I think as scientists we just should hold ourselves to a high regard in terms of capturing the actual mechanism of a problem. And in that case, it doesn't matter if you're sacrificing accuracy or not. But it's still
Yeah, thank you.
Uh,
Yeah, I think actually you answered my question, and
okay.
I think interpretability is actually quite important for machine learning models in some cases. So yeah, thank you.
That's one thing, and also just generalization. So just not, which is also what causality is about, just not using confounding data, for example, to arrive at a prediction also gives you a lot of robustness.
Hi, Dan.
Yeah, that's
Aris?
for sure.
Yes, I have a question. Thank you for a very thoughtful presentation, Dan. So I'm thinking of problems whereby we would like to predict something, but we have a question whether the observations we have are adequate for that. It's a question of observability, actually, of the system. That's what in the classical sense of systems analysis. So when you say in the initial part of the talk, you talked about being able to use the forecasted parameters for the rockways, for example, and you had a list of those to predict the heights. How do we know in a case of a complex system? How do you know whether the observations you have are adequate to give you to be able to give you this prediction and therefore not to be able to discover the causalities that underlie the process? Versus a case where you don't have enough observations, you're just doing a black box things. You're developing a model that's basically is poppycock, because if you change the data set, you're not going to get anywhere because the system is not observable enough to allow you to make the predictions. So this problem of observability of the system, given the data you have, how do you address it?
Yeah, okay, yeah. Thank you for the question. I think that I could talk for like another 40 minutes now. I'll try to keep it concise. I think there's a couple of extenuating factors, like when it comes to that application specifically, where it's like, okay, we want to predict a rare event that is also probabilistic. So we know that there's probably no condition that will always lead to a rogue wave. And that is also somewhat unknown and susceptible to noise. So there's like 4 probabilistic noise variables or so, at least in that system. So how do we even know if we have enough data to make a statement about the very low probabilities that we're forecasting, first of all? And second of all, how do we know in a general case? Like, and I think for this problem specific, so I only presented now the last publication in that arc, and there was at least one before that where we looked at that, what I think very diligently, or I tried to be at least very diligent, and really quantified this uncertainty. So for example, it's a lot easier to quantify that post hoc, because in probabilistic systems, I like to illustrate that with like a very artificial example, but for example, for a coin flip, there's no experiment that can tell us if the coin is fair, so it's a 50% probability for heads or tails, or if there's actually a little demon inside the coin that decides the flip deterministically, but that just has its own stochasticity. So I'm making that point because it's not in probabilistic systems, there's always unknown unknowns that you cannot quantify. So with that caveat out of the way, you can look, for example, at the calibration of your model. So if your model predicts a chance of 1 in 1,000 of an extreme event, and then you look at that and compare it to the measured frequency, then you get a calibration curve, essentially, in different bins of that prediction, range of prediction. And that's one thing you can look at. And then you can also look at essentially different binnings of the parameter space and see if your model makes a good prediction or not, based on the uncertainty that's implied by the number of samples you have and by the low probabilities that you're forecasting. So we did, if you want to read more on that, we have a whole publication on it, where it's really about quantifying that in a Bayesian way in different parameter bins, and then suggesting that we actually do have enough data despite the low probabilities.
Okay, thank you. Yes.
Any more questions online? Okay, let's move to the audience here in the classroom. Max?
Thanks for the talk. My question is a bit how, when you were interacting with the models to output the data in each individual model, how did you actually go about getting it to generate the data? Were you using prompt, like a specific template for each model, where you asked the same questions, or what was your method of getting it to generate what it output? As well as that discovery that you made in the end of the equation, did you fit that to like a sequence of numbers, or how did the model output that, or how did you come up with that equation?
I'm not sure if I understood the first question, but not not conceptually, I think. Since you were talking about prompts, so do you have something like an LLM in mind or so?
Yeah, I guess maybe my understanding is not really fully, because my experience with it is really just using ChatGPT in that way.
Oh, I see. Yeah. Oh, I should have opened with that in my talk, because I think that's exactly like the kind of AI narrative that's confusing a lot of people, and it's understandable that you are confused, because that's what's the talk of the town and very exciting. So LLMs is really something that I think is not applicable in this kind of scientific inquiry, where it's really, for me, I like to view AI more as a data analysis tool, and like for data mining and pattern recognition, where this is just like fundamentally at odds with the way LLMs work, and like next token prediction and hallucinations, and the immense data and compute requirements. So none of what I showed today is using LLMs. It's actually just regular neural networks trained by myself on that numerical data, and not on something like a word model.
Any other questions? Yes, please.
I really enjoyed your talk. Thank you. I think a lot of the people in the room empathize a lot with what you're saying about kind of the narrative around AI and what's actually useful and what's kind of superfluous. But I have several questions, but I just ask one. Many scientific questions, or engineering questions in particular, may not have the sense of causality at all, right? You can imagine like an inverse problem may not have any sense of causality, or you may observe an observation that is the cause of something you don't observe, similar to the observability question, and be trying to make predictions based off correlated observations rather than observations that would yield something. Do you feel that these symbolic regression kind of interpretability tools like have a place in those kinds of problems, or kind of what's your thought on kind of that class of problems in general?
Okay. I would like to challenge this notion that I think there's very few problems that are acausal in any meaning of the word. Sometimes the causality is extremely complex, so it's intractable. I mean that I can accept. Or there's control systems where there's essentially cycles in the causality. So which is also a way of intractability. So I think the arrow of time that is prescribed by the universe does define causality always. It's more about, okay, there are systems where that causality is not available to us, and which might be just a philosophical difference. I think a good example for that is turbulence, where people have made the point that, well, now we've tried for decades, centuries to write down a good model for turbulence that works at large scales. And now we're applying machine learning to the same task, and there are attempts to learn turbulence closures from data with symbolic regression or similar methods. And it's going okay. Sometimes you discover something that works a little bit better, but it's still elusive. So I think there is a class of problems that just might be incomputable in a way, with like these concise mathematical equations on like the macroscopic level. And yeah, sometimes you might just have to actually simulate microscopic dynamics. So I wouldn't say that symbolic regression or even like mathematical modeling in that regard is something like a silver bullet, but I think it should be the first thing to try. So if I come up with a very strong model, or even like a black box model that predicts turbulence well, I think it's a logical next step to try to understand, how does the model work? Why does AlphaZero not play the French defense anymore? And if there's tools to get at that question, and there's actually, yeah, I'm wary of going off the tangent, but there's a follow-up paper from DeepMind with like the former chess world champion Vladimir Kramnik, just analyzing AlphaZero, and that paper is much longer than the AlphaZero paper. So I think there's interpretable AI is a little bit of a dead end to me, because it might be, okay, some classes of problems might just be not computable in these concise representations. And for all others, you can use something like symbolic regression to at least give it a shot. And symbolic regression is also plagued by the fact that these problems are really NP hard. So there's a combinatorial space that you're trying to explore, and most of the time you're not gonna discover something useful, but sometimes you just might. And I think it's just something that's generally very underexplored and underutilized.
Thank you. Could I ask a second question?
Yeah.
I'll let Ian go first. Thank you. I think that answer makes a lot of sense.
Thank you.
Hi, I had a question. So, well, I accept that having an equation is nice. But I would argue that an equation isn't quite an explanation. That where the explanation, where the science comes from, is getting a derivation to that equation. Now, there have been examples in the scientific literature, of course, of an empirical equation that then eventually became explained, like Dulong-Petit comes to mind. But most of those have been, if not all of them, have been in situations where it's so simple, the equation at least, that you wouldn't think to use a neural network to do that. So how confident are you that these equations that you're generating can eventually have derivations?
Not confident at all, and very confident in other ways. I think it's a little bit of a false dichotomy to think, well, equations, and I totally agree with an equation is not an explanation, at least not until we fully understand it and maybe can derive it from first principles. I think it can become an explanation, and it's the kernel of one. And I have zero confidence that the exact equation that we discovered is even explanatory in its majority. But that's also a point that I was trying to make when I was presenting like the state of the art in research on that phenomenon, where it's like, okay, we have 4 conflicting theories. We can't really select among them because they're like describing slightly different things and might be very describing, for example, idealized physics in a way. So I think it's in this case, the most beautiful result for me was really to rediscover one of those hypotheses within the learned model. And I think that gives a lot of credibility to that particular theory, plus gives us a couple pointers on where to look next on like extensions and like second order effects that might be playing into that. And I think it's not a full explanation, but it's at least, I would argue, a part of the scientific process to just add your pile of knowledge to the research canon, and then maybe pass the baton to the next person wanting to look into specific things. And I think that's this incremental way of conducting science is just something that's enabled by that, and that's much, much harder with something like a black box model.
Yes.
Yeah. Thank you for the talk. Thought it was super interesting. I liked how you mentioned GNNs. I think graphs are very useful for, depicting any sort of like geometry. And I liked how you mentioned that there are those issues with more complicated geometries and sometimes being too constrained on rollout with the message passing. I was wondering if you had tried, or what your thoughts were on some of like the dynamic remeshing approaches during rollout used by like mesh graph nets or similar models, if you guys have tried that, or if you had any thoughts on how that might work for these more complex situations.
Okay, yeah, that's very on topic and something that we think about a lot. Yeah, I really love the MGN Piper, and dislike certain parts of it at the same time, where I think it does a fantastic job of like showing what the ceiling is with like these things like adaptive remeshing and like showing a flapping flag in the wind or so, that are very inspiring, like from a capabilities point of view, but also gloss over so many practical issues with actually doing something like that in a real world setting that is almost unusable in its state as it's presented. So but in a way I think that's fair and okay for a research project to be in, to like show people this is the dream, and then yeah, sure, then there's going to be a lot more to actually make that usable. So as someone who has looked extensively at MGNs, we're still very far from doing something like adaptive remeshing. Especially, it's important to keep in mind that a surrogate model isn't done when it's trained to good accuracy, or like when it's able to simulate a certain phenomenon, but it also has to be cost effective to even justify the immense cost of training a model and generating the training data in the first place. And I think this cost effectiveness is where most model architectures die, where just so many things tie in, like to how efficient things are to compute on GPU or like other hardware, and that is a very, very difficult thing to pull off to a really cost-effective surrogate model, which is also one of the reasons why we just explore all of these different dimensions of how to use surrogate models. So not just to be more cost-effective, but also to allow completely new things to be simulated, where no amount of money today can buy you a simulator. I think that's something that's extremely exciting, but also a very long way to get to operational.
Thank you.
Dion, thank you very much. It was an amazing presentation, a lot of questions. So I will follow up with you via email.
Yeah, let's do that.
Much for being here. It was a beautiful talk and great interaction with the student here. Thank you very much.
Yeah, thank you for having me, and I really enjoyed the questions and the audience. So yeah, thanks all.
Thank you. Bye-bye.
Bye.